Hey guys, this is Professor Janacek, and I want to talk about divergence of a vector field. Before we start with that, let's talk about something called the Dell Operator, also sometimes referred to as nabla. The notation for that is looks like an upside down uppercase delta. And the way we do this, it works on a vector, and we'll take the partial derivative of the first component of the vector with respect to our first independent variable, in this case x, the partial derivative of the second component with respect to y, and the partial derivative of the third component of our vector with respect to our third independent variable, in this case z. Of course, if we only have if we're only working in 2 dimensions, then we don't have to worry about the third component or that third variable z. So what is divergence? Well, for a vector field f, the divergence of f, and there's the notation for it, is the dot product of the Dell operator with our vector field. Now, before we talk about how we actually do this, let's talk about what divergence gives us. Divergence measures the expansion or contraction of a vector field at each individual point within that field. So how much is it expanding or contracting at any given point? Now, if our divergence value is positive, then that vector field is really acting as a source. And if the divergence is negative, then the vector field is acting as what we call a sink. So a source, of course, is emitting, and a sink is would be contracting. So a source is expanding, and a sink is contracting. So let's talk about what this looks like. How would we work this in a two-dimensional situation? We would have the vector field f would look something like, let's call it f comma g. So it's a vector field in R2. It has 2 components. Then the divergence of f is the partial derivative of f with respect to x plus the partial derivative of g with respect to y. If we're in 3 dimensions, then our f vector field would have 3 components. Let's call it f, g, and h. And then the divergence of f, we're going to take the partial derivative of f with respect to x, the partial derivative of g with respect to y, and now the partial derivative of h with respect to z, and then we will add them all together. So notice I'm taking the partial derivative of each function, but only with respect to one variable. I don't have to take the partial derivative of f, say, with respect to y or with z. Now, if the divergence of a vector field f is actually equal to 0, notice that's the scalar 0. Divergence is a scalar value because it's a dot product. Then we can say that the vector field is source-free. Again, if the divergence is equal to 0, then we say that the vector field is source-free. All right, let's take a look at an example here. Let's see if we can find the divergence of our vector field, defined with the first component of e to the raised to the negative x plus y. The second component is e raised to the negative y plus z, and the third component is e raised to the negative z plus x. First thing I want to do is let's identify our functions. Because this is a vector field in 3 dimensions, let's go ahead and name our 3 functions f, g, and h. So we'll label f of x, y, z as e to the negative x plus y. G of x, y, z is equal to e to the negative y plus z, and h is our third component. H of x, y, z is e to the negative z plus x. So what is the divergence of f? Well, again, we're going to take the partial of f, just with respect to x though, not with respect to y or z, plus the partial of g with respect just to y, not x or z, plus the partial of h only with respect to z, not x or y. So what do we get here? Well, notice I'm going to take the partial of f with respect to x, which, by the way, using the chain rule, we get negative e to the negative x plus y. The partial, by the way, of g with respect to now just y is also negative, but this is e raised to the negative y plus z. Again, we're using the chain rule here. And the partial of h just with respect to z, oh, look at that, also a negative, e raised to the negative z plus x. Thus, the divergence of f is equal to negative e to the negative x plus y plus a negative e to the negative y plus z plus negative e to the negative z plus x. Obviously, we could, if we wanted to factor out that negative, and so we have negative e to the negative x plus y plus e to the negative y plus z plus e to the negative z plus x. Again, all we're doing here is simply adding those three first partial derivatives. And there you go. That is how we find divergence. Enjoy!